Okay, so next up we actually have two related talks. So Lasse is going to give the first talk, and then we're going to switch over to Boss for two related papers where one builds on the other.
Thank you. Yes, so I'll start by introducing what I've been working on here. So we'll start by talking about why we are looking at smart contracts and why we actually want to formalize smart contracts. So first, what is a smart contract? So a smart contract is a computer program or a transaction protocol that is intended to automatically execute, control, or document events and actions according to terms for a contract or an agreement. And the primary idea is that we can actually specify and execute things in a very precise manner. However, sometimes these implementations of smart contracts actually go wrong. So we would actually want to specify these or formalize them. And furthermore, we can see that there's actually getting a more push for doing these formalizations. So the Data Act for Smart Contracts says in one of its subsections about robustness and access control that you need to ensure that smart contracts avoid functional errors and withstand manipulation by third parties. So what this actually usually looks like is that you're doing a lot of testing of the smart contracts to ensure that they're not doing anything wrong and you're just doing validation by inspection. However, as we're getting better tooling, we think that you should use formalization for actually doing these things. And we'll show how we do this. So first, a bit about the landscape. So smart contract languages have developed over a long period of time. So they started out with the Bitcoin language, which called script, which was not a fully Turing complete language, but just done for simple scripting. And then we got a more expressive and more modern blockchain like Ethereum, which uses Solidity, but Solidity is not the best thing to code in. So more blockchains have developed and more layers on top of Solidity has also been, or on top of Ethereum has also been made. So, for example, we now have examples of smart contracts using Rust and WebAssembly to actually run. So, for example, the Concordium blockchain is using Rust as a smart contract language, and Ethereum using rollups is also using Concordium, or also using Rust with WebAssembly as backend. And others are like Polkadot, ICP, Cosmos, Near, Hyperledge Sawtooth. So there are many examples actually using this. And the different goals of many of these are also a reason that there are so many different blockchains. So here, some goals could be performance, developer experience, how the quality of the blockchain, and interruptibility between different blockchains. So some build that on actually being able to interact with different blockchains. And we even have languages, functional languages for some blockchains. So like Plutus, Icon, and Cardano are a functional language for Cardano, and Cameligo is a functional language for Tezos. Yes. So we want to say that given this landscape, we can actually do the specification and implementation of smart contracts in the HEX framework. So the HEX framework is provides a language which aims to be a middle point for a lot of people. So it aims to target cryptographers, proof engineers, and software developers. But it also has these backends to CoQ, EasyCrypt, and FStar, and more backends are being added. It tries to make internet standards machine readable, and it's a simple subset of Rust. However, you might say, why would we want to use HEX if it's targeting cryptographic specification? However, here we want to say that specifying smart contracts actually aligns very well with this space, as we also want machine readable specifications that you can test against. This being a subset of Rust is also a very nice feature, as many smart contract languages are using Rust. And we also want to have a community where we can collaborate between people actually implementing the code and having some formal validation of the specifications. Yes. So if we want to look at an example now, so if we're given some smart contract in Rust, what we would want to first do is take this smart contract written on the side here, which takes a context and a state, and then it returns some actions for the contract. So what we then do for translating into HAXspec is that, or into Hax, is to do message state passing instead of just having the mutable state. As HAXspec is a functional or semi-functional language, so we don't have a mutable state in the language. So you would have to refine your contract to actually fit inside the subset to do the first step of this specification. This allows us to actually do proofs about functional correctness. However, we don't just want functional correctness for our smart contracts, we also want cryptographic security, as many of these smart contracts build on cryptographic primitives, so many use zero-knowledge proofs and things like that. So we would want to get also cryptographic security of our implementation. And one way we're actually doing this is using the SS-proof framework. So SS-proof is a foundational framework for doing modular cryptographic proofs inside of Coq. It takes and embeds a probabilistic stateful language inside of Coq, and it uses the Dijkstra monad framework to give us a way to reason about these programs. So you can actually take the code generated by Hax and reason about the cryptographic security of that inside Coq. So this is also now a backend of Hax. This was work presented at CPP, adding this backend to Hax. And this allows us, as I said, to do better security proofs of these contracts. However, we are only doing security proofs for like individual functions and not more broadly the state of the smart contracts. So how does this translation actually look? So we are translating into the equations definitions, and the reason we're doing this is because a lot of the translation is using proof obligations. So we are solving all of these proof obligations about how things move around in the flow of the original program. Specifically, we can look at things like proving the validity of the programs of SS-proof can be solved automatically using these equations. As the Hax language is very simple and structured, so it's easier to do a lot of automation on actually validating the code. And this also allows us, as I said, to show security properties about individual functions. Now for going beyond just individual functions and looking at more general interactions, so a contract usually uses a lot of state. So if we want to look at how the state changes over time and ensuring that we are not doing anything wrong, entering in a bad state or anything like that, we are using ConCert. So ConCert is a smart contract certification framework in Coq. It facilitates property-based testing of smart contracts using the quick check library, and it has extractions to Rust and Elm and so on. What we are using it for here is taking the SS-proof code and actually doing testing on that. Yes. So we can now look at why we are doing this embedding into to ConCert instead of taking and just extracting from ConCert, as it has extractions directly to Rust. So we could just specify our smart contracts inside of ConCert and then extract to Rust instead. So what we want to say is that embedding actually gives us better looking code. So if you just take the extracted code from ConCert, it produces a non-idiomatic Rust code. So for developers actually working with this, it's hard to continue working or building upon code generated. Furthermore, the embedding also allows us to annotate the code and add features from the Hax toolchain on top of just the smart contract code itself. So by annotating the hex code, we can automatically translate some of these annotations about the message passing and the initialization of the smart contract into ConCert, and inside of ConCert we can then wrap this behavior inside a contract type, which allows us to just look at the behavior of the contract isolated in ConCert. So we can actually do some proofs of traces of behavior, and we can do property-based testing of these things. And furthermore, we connect these annotations up to existing libraries. So yeah, so what we're doing to achieve some of these things, to actually meet developers where they are, is that we take smart contracts and embed them inside of Rust instead of extracting from ConCert, as this gives us better looking code. We take annotated properties for tools. So we take and annotate properties inside of hex to get extractions to tools and extractions with tools. This can look like a quick check where we have specified inside of hex the quick check properties, and you can test them directly in the Rust code layer, but you can also translate this to Coq and do a quick check testing inside of Coq and validate that you're actually getting the same results as you were doing for the testing on the original layer. So we have this multi-layer tooling connection where we both have the tooling on the Rust layer but also on the Coq layer. And this also extends to tooling for Creusot or CoqPL'24 language, where we have specified annotations inside hexspec or inside hex, which is then taking the subset of CoqPL'24 that fits in within the subset of hex and translating that to Coq. And then we can take the proof application generated there and actually validate that the proof applications are doing the correct thing, like validating proofs, where Creusot just checks them in Y3. Yeah. And lastly, we can use the entire ConCert framework to actually reason about and encapsulate the behavior of smart contracts as a whole. Thank you. Questions?
I have a question. So, how much of this do you think developers, how much of the specification do you think developers have in their head versus would need help figuring out? I mean, do developers have a more abstract perspective on their contract?
So I think developers know a lot about what guarantees they expect from the contract, but they will probably require a bit of like getting used to a training for actually just taking the abstract model they have and actually writing it down in code and specifying it. But I think this is a good step towards getting used to that, because you actually put the specification in the hands of the developers and not just having it as you have to have proof knowledge in Coq to actually be able to do these things. And it also allows you to do like automation, as a lot of these annotations for the developers and getting some of these properties written down allows you to see what the class of problems you actually want to automate, and the class of problems that are very general for these smart contracts. Yeah.
Any more questions? I'll ask one more question. So do you have examples of, like, what examples have you done so far?
Yeah, so...
And what do the proofs look like?
So we have a couple of very simple examples, and then we have the next talk as a good example also. So examples basically look like a 1 or 2 lines of annotating properties on the smart contracts. And the extracted code it's readable. It's close to the surface level code, but there is a bit of extra annotations to actually translate these things. We have actually been able to show security properties using this framework to translate. So for other protocols, not smart contracts, we have done the entire translation and shown realistic security properties for something like AES. So you could expect, like, if you have smart contracts with AES as a sub-protocol, you could actually extract and validate that using this framework. However, extending that, we can also look at the extracted code for the smart contracts itself and do proofs on that. However, we haven't done that for any examples yet, but we expect to get a library of examples soon.
Okay, then let's thank the speaker, and Lasse, you can get set up.